Prove each statement in 8 through 23 by mathematical induction. 1 plus 3n is less than or equal to 4 to the n for every integer n greater than or equal to 0. So the first thing I'm going to do is I'm going to identify what p of n is. P of n is going to be the inequality 1 plus 3n is less than or equal to 4 to the n. So the first part of our proof is to prove that p of n is true for our base case, which is the smallest integer that satisfies the statement p of n. And in that case, that's 0. So first, let's identify what that statement is. I'm going to rewrite p of n, but I'm replacing all of my n's with just 0. But I'm also going to put a question mark at the end of this so that I avoid assuming my conclusion. This is the thing that we want to show in our base case. And to show that, we can evaluate both sides separately. So the left-hand side is equal to 1, and the right-hand side is also equal to 1, and 1 is less than or equal to 1. And so that's us verifying that p of 0 is true. So the beginning of our inductive step is always going to be the same. We're going to say let k be an arbitrary integer with k greater than or equal to 0, and assume that p of k is true. Let's unpack what p of k is. This is our assumption that we need to use to prove that p of k plus 1 is true. So I'm going to take p of n, and I'm going to replace all of my n's with k's to get 1 plus 3k is less than or equal to 4 to the k. We get to assume that this is true for a specific value k. And now we're going to prove that p of k plus 1 is true. So this is our goal. Now we get to use our inductive hypothesis here in blue to show this. But how do we do that? Well, let's start with the left-hand side of this inequality. Now our inductive hypothesis makes a claim about 1 plus 3k. If you notice, 1 plus 3k is in this left-hand side of p of k plus 1. And so I'm going to rewrite this as 1 plus 3k plus 3. Now, I know it's tempting to combine this 1 and this 3, but if we want to use our inductive hypothesis, we need to separate this 1 plus 3k over here, because now we can say that this 1 plus 3k is less than or equal to 4 to the k, and then we still have this plus 3. So I'm just making this portion right here bigger using the inductive hypothesis. It's important to note where you use the inductive hypothesis, and that's specifically with this inequality here. But this is not quite what we wanted. We want to bound this by 4 to the k plus 1, not 4 to the k plus 3. But once we apply the inductive hypothesis, we're usually just a few steps away from the solution. The way we get to the solution is to replace that 3 with something bigger. We're going to replace 3 with 3 times 4 to the k. Now, 4 to the k is bigger than or equal to 1. And so if I replace 3 with 3 times 4 to the k, I'm making the overall number here bigger. And now we can factor out a 4 to the k. It's 4 to the k times 1 plus 3, which is 4 to the k times 4, which is 4 to the k plus 1. Okay, let's review. We started with the left-hand side of p of k plus 1, showed that it's equal to this, which is smaller than that, which is smaller than this, which is equal to this. And so overall, what we showed is that 1 plus 3 times k plus 1 is less than or equal to 4 to the k plus 1, which means that p of k plus 1 is true. And that's the end of the inductive step. At this point, we can say the ritualistic conclusion of all mathematical induction proofs, that therefore by mathematical induction, the statement p of n is true for all integers n greater than or equal to 0. Thanks everyone, and I'll see you in the